we should be clear about the terminology. We are talking about speech and language. What is speech? By speech, we really refer to the speech signal, to the waveform, and by language, we mean the text or written language. And a characteristic property of speech recognition is it's a well-defined task due to the fact that we have a 5,000-year history of the writing system for languages. And we have well-defined classes. These are the letters or words of the language. And we consider this to be an easy task for humans, at least in our native language. And the last 50 years have shown that it's really a hard task for computers. And it's interesting to note that the term artificial intelligence came up in this context. Originally, it meant a computer program that performs typical human tasks like speech recognition and language translation. So in all these cases, we are facing a sequence-to-sequence processing problem. We are given a waveform as a speech signal, and this has to be converted to a sequence of words or characters. Similarly, for machine translation, we start from the words in the source language and want to convert this into a sequence of words in the target language. And the other tasks that fit into this concept of sequence-to-sequence processing, like handwriting recognition, natural language understanding, also text-to-speech synthesis, and also sign language recognition. This is my view of the history, simplified history. Early work started already 50 years ago, and the most successful approach has turned out to be machine learning. That means a probabilistic approach where the machine tries to learn from data. So this amounts to a lot of statistics, and the requirement here is that we have annotated data available. Annotated data means we have pairs of input-output sequences, parallel sequences. And the requirement of progress was that we have data, computation power, and good models and algorithms. And it's true, there has been a huge progress due to artificial intelligence and deep learning over the last 30 years. So that really started 30 years ago and not just 5 to 10 years ago, as many people tend to think. The general framework here is really machine learning and probabilistic modeling, but we have to keep in mind that neural networks define just one method in the framework of probabilistic modeling and machine learning. So here you have the typical architecture of a machine learning system applied to speech and language processing. There are many blocks. I cannot go into details. The most important blocks here are probabilistic models and numerical optimization. And in order to carry out numerical optimization, we make use of the training data. And then data are used again in order to evaluate the quality of our models. And it's really in these two areas, probabilistic models and numerical optimization, that we have made most of our progress over the last 30 years or so. I think I will skip this for the sake of time. So let's look at a specific task like speech-to-text translation. So here we really want to go from the speech signal in the source language to text in the target language. So we skip sort of the level in between, namely the text in the source language. If we carry out these two operations, speech recognition and machine translation, sequentially, then we talk about a cascaded or sequential architecture. We might also use a direct architecture, integrated architecture, where we try to go directly from the speech signal in the source language to the text in the target language. In all these cases, we are facing two important scientific challenges. Namely, how can we counteract the propagation of errors from the ASR component to the MT component? And then, typically, we are given three types of training data, namely a fair amount of training data for the ASR component, a large amount of data for the text-to-text machine translation component, and only a small amount of data for the speech-to-text MT component. And the challenge is really to design methods, algorithms that are able to exploit these three types of data as much as possible. And we can go one step further and include TTS. Oh, the pointer does not work, okay. So this is the lowest, the block at the bottom, where we go from the text in the target language to the speech signal in the target language. And in that context, there's a specific challenge about TTS, namely expressive voice. What do we mean by that? In the speech signal in the source language, the speaker has characteristic properties, and we would like to transfer these properties into the speech signal in the target language. And this might also include the emotions of the speaker. And evidently, if this really works, there are many applications, human-to-human communication, dubbing for in movies, and also voiceover in documentaries and news reports. So the methods that I've described so far, they rely on what you could call supervised training. As I said, we are given pairs of parallel input-output sequences. This is a standard method for today's research systems and also commercial products. The disadvantage is that we need a huge amount of manual annotation. This is expensive. And as opposed to that, we might consider unsupervised training, where we are given two independent sets of data, let's say audio or speech data for a specific domain in a language, and similarly just text for the same domain in the language. And the advantage is we do not need any annotation, and we can have huge amounts of data. This is really the advantage. No annotation is needed. Of course, the scientific challenge is to make it work. I mean, there's already ongoing work in research prototype systems, but still we need further improvements. And then if this works, we can move to commercial commercial production systems. You might also think of a combination of the two methods, semi-supervised training, where we have a small amount of annotated data for supervised training, and combine it with unsupervised training, where we really can use huge amounts of data without annotation. I described this concept mainly for ASR, but it similarly works also for MT. So let me summarize. Yes, we have made a lot of progress. Today's systems work, but they have still many shortcomings, like low accuracy, lack of robustness. We have systems only for a few languages. So in my view, the future trends will be that we should have more real-life data with large variability across different types of conditions, like speaker, accents, dialects, acoustic conditions, and so on. And the present systems, the present solutions that we have are fragile and brittle, in particular when we talk about their robustness concerning domain context and acoustic conditions. So in general, the algorithms must become better in order to handle these problems. We need multilingual solutions. We have to cover many, many languages. I talked already about unsupervised training. And what we need in general is improvements in methods for machine learning. And in order to do that, yes, we need data. But we should keep in mind that neural networks define just one out of many possible structures in the area of machine learning and probabilistic modeling. And this, in my view, remains the fundamental challenge to get better models of the complex mathematical dependencies between input and output sequences. That's all. Thank you very much.